All right, today we're going to talk about converting concentration units, then we'll look at some graphs, and then lastly we'll take a look at some types of solids. First of all, converting concentration units. The first concentration unit we're going to talk about converting is percent by mass to molarity, capital M molarity. Here's the sample problem. We have hydrochloric acid in its concentrated form. When you purchase it, like at Fleet Farm, it's called muriatic acid, and it's 36% by mass. The density of this solution is 1.27 grams per milliliter. Change this, or calculate, its molarity. So step number one is to take a look at what we want to know. We want to know molarity, and molarity is equal to moles divided by liters. And so we need to use these two pieces of data right here to help us find moles and to help us find liters. So let's look closer at what each one of these things finds, or calculations for them, to see if it will help us find the molarity and help us find the liters. First of all, percent by mass. We know that it's 36% by mass, and this would be the mass of the thing that I'm interested in, so the grams of HCl, divided by the total grams of the solution. The total grams of the solution. So if I found the grams of HCl, that would help me a whole bunch, because then I could convert that to the number of moles of HCl, that is, by using the periodic table. So that's my goal to find, and all I need to know is the grams of solution. And remember, percent, you always multiply by 100 right here. So that's goal number one. Goal number two, how do I find the number of liters? Well, it tells me the density, and density, remember, is equal to mass divided by volume, and liters is a volume. So if I found the volume right down here, then that would help me find the number of liters, because I could find the volume in liters. So trickiest part of the problem is to make an assumption, and the thing that I want to assume is an amount of a sample. And I'm going to assume a 100-gram sample because that's a really nice round number and it makes things really easy. If I assume a 100-gram sample, then all of a sudden I can put that 100 grams in lots of places where I need it. I can put in a 100-gram sample as my total grams of solution, and now 36% is equal to my grams of HCl divided by 100 grams of solution times 100%. Now the math all of a sudden becomes really easy, because this 100 cancels with this 100, and how many grams do I have? 36 grams. Now I can take this 36 grams and I can convert it to moles by looking on the periodic table. And on the periodic table, chlorine is 35 and hydrogen is 1. So if I add 35 plus 1, I now have my molar mass of 36 grams in 1 mole. Ooh, the math is really easy. 36 divided by 36. It's approximately 1 mole of HCl. Now that goes right up here in my calculation. I know the moles. Second of all, I got to find my liters of solution, and I use my density to find that. Density is equal to mass divided by volume, and the mass of my solution I just assumed. I assume that I have a 100-gram sample. My volume of my solution I need to know, and in the question it tells me that the density of the solution is 1.27 grams per milliliter. So to solve this equation, multiply both sides by V, divide both sides by 1.27, and so then volume is equal to 100 divided by 1.27, which if you punch that into your calculator turns out to be 78.74 milliliters. That goes in here, except it can't be in milliliters. I have to convert it from milliliters to liters. So punching those two buttons now, my moles are 1 mole, and I'll need to divide that by my liters, which 3 to the left, 123.07874 liters. Dividing those guys turns out to be about 12.7 molar. If I go to 2 sig figs, which I only have 2 sig figs right here, it would be 13 molar as my concentration. These steps are one problem on the test. The second type of conversion I need to do is my mass percent and parts per million and parts per billion. Mass percent, parts per million, and parts per billion. All three of these are calculated the same way. I take my mass of my component in my solution, divide it by my total mass of solution. I always say it's easiest to have the mass in grams and the mass in grams, because then you know the grams will cancel with the grams. And then you multiply it by this box right here. Now, if it's mass percent, you always take percents and you multiply them by 100. So if it's a percent, just take and multiply the mass divided by the mass times 100. If it's parts per million, now take and multiply it by 1 million. Instead of 100, you multiply it by a million. If it's parts per billion, you would multiply it by 1 billion, or a 1 with 9 zeros after it. So mass percent, part per million, and part per billion are always the same equation. It's just the number that you multiply it by when you're done. So let's do an example problem. The EPA regulates water sources, and it says that water that people drink are limited to 15 micrograms per liter in parts per million of lead. 15 micrograms per liter of parts per million lead. Okay? I'm sorry, not 15 parts per million, 15 micrograms. I'm sorry if I said parts per million, that's my fault. 15 micrograms per liter of lead. Calculate this in parts per million. So we need to change it from micrograms per liter to parts per million. So using this equation right up here, what I need to do is take my mass of my component, the mass of my lead, put it in grams. So parts per million would equal 15. Now it's micrograms, so I want to put it in grams. And micro means 10 to the negative 6th. So 15 times 10 to the negative 6th grams. And then divide that by my total mass of solution. This might be tricky for some people. It says there's 1 liter of solution. 1 liter. And you do need to know that the density of water in most aqueous water solutions is 1 gram per milliliter. That's the density of water. If you don't know that, take your arm and write in Sharpie right here, right along your arm, and then it'll always be there. 1 gram per milliliter for density. Since I have a liter, I have 1,000 milliliters, and if each milliliter is 1 gram, then I have a total of 1,000 grams. So 1,000 grams, or 1 times 10 to the 3rd grams, is the mass of my total solution. So mass of component divided by mass of the total solution, and then multiply that by, well, it's parts per million, so it's going to be times 10 to the 6th. So if you're multiplying two things together, what do you do with their exponents? Add them. 10 to the 6th go away. So it's 15 divided by 1,000. This just means move it 3 places to the left because I'm dividing by 1,000. 3 zeros. So I end up with 0.015 parts per million. Now in Flint, Michigan, when they actually came in and measured some of the lead concentrations, they measured them in parts per million. I believe there were some samples that were on the order of 200 parts per million. So people were drinking water that was quite a bit above what the EPA regulations were. Not all of them were like that, but some of them were. Those are the 2 types of conversions that you're going to need to be able to do for concentration. Second item is you need to be able to determine solubility changes with temperature. Solubility changes with temperature. For solids, solubility generally goes up as temperature goes up. As a matter of fact, if you look at the little graph in your book, looks like this guy right here. This is on page number 543. If you want the color version, you're going to have to look in your book, but I'm going to zoom in on this one. You can see that as the temperature increases to the right, the solubility curves generally increase up and to the right. And so the solubility in grams of salt per 100 grams of water generally increases up and to the right. There's a one exception right here, but for the most part, as it becomes higher in temperature, more stuff dissolves. So here's a couple of trick type questions that'll show up on the test. Let's say, for example, we have a beaker, and the beaker contains 100 milliliters of water. Okay, that fits right in with this because 100 milliliters is about 100 grams as long as it's density of 1 gram per milliliter. Inside of that, I'm going to take and dissolve, or I shouldn't say dissolve because that's the wrong word. I'm going to take and I'm going to place inside of this beaker 30 grams of KClO3 solid. And I'm going to happen to do this at 30 degrees Celsius. Okay, so my question for you is, please define this resulting solution. Is this resulting solution saturated, unsaturated, or supersaturated? Saturated, unsaturated, or supersaturated? Well, let's read on the graph and let's see if we can figure it out. It says it's at 30 degrees, so look at the temperature right here. Here's 30 degrees, okay? And it says that I have 100 grams of water, so it's okay to be on this scale right here because it's 100 grams of water. And I'm going to dissolve 30 grams of KClO3, so follow this up until I get to 30 grams. I'd be right here. Okay, am I at the solubility line of KClO3? How much should really dissolve of KClO3? 10 grams should dissolve. So, is the solution, and careful, listen to my words carefully, is the solution saturated, unsaturated, or supersaturated? Take 5 seconds right now and turn to your neighbor and justify your answer. Ready, set, go. Okay, the answer might surprise you because remember the question that I asked is describe the solution. That's the liquid part that's inside of this beaker. The liquid part inside of this beaker would be a saturated solution. And you're like, oh, but you put 30 grams in there. Yup, that means 20 grams, the difference right here, is sitting at the bottom of this beaker doing nothing. There's some solid sitting at the bottom of this beaker that's not dissolved. 20 grams of it that didn't dissolve. But remember, I asked to describe only the solution. And the solid that's sitting at the bottom of the beaker is not part of the solution. It's a solid just sitting there. The solution is just the liquid portion right here. And 10 grams dissolved in it, and that's a saturated solution. So be careful of that tricky question when it gets asked. Now let's take this solution and let's heat it up. The 30 grams of KClO3 is still in the solution. We still have 100 grams of water. It's at 30 degrees Celsius, but now I'm going to heat it up. I'm going to heat it up all the way to 90 degrees. All the way to here, 90 degrees. When I heat it to 90 degrees, now is the solution saturated, unsaturated, or supersaturated? 10 seconds, turn to your neighbor, justify your answer. 3, 2, 1, 0. The answer is, if it were at this point, it would be an unsaturated solution. Unsaturated because I'm below this line here of KClO3. To make it be saturated at this point, I would have to go all the way up to here and dissolve maybe like 45 grams or something like that, but I only have 30 grams dissolved in there. So if you said unsaturated, you're correct. Now take this solution and let's cool it down. I still have the 30 grams of KClO3. I still have 100 grams of water. It's at 90 degrees. I'm going to cool it all the way down here to 40 degrees. Cool it to 40 degrees. Now, you don't know this, but KClO3, when it dissolves in water, is a clear solution. You can see right through it. It's just like looking at water. When I cool this down, the solution still looks exactly the same. It's a clear solution. There's no solid in it. It just looks like pure water. So at this point, right now, at 40 degrees Celsius, is this solution saturated, unsaturated, or supersaturated? 10 seconds, tell your neighbor, justify your answer, go. At this point now, since you didn't see any solid form, you would have to say that this solution is supersaturated. Supersaturated because I have more dissolved in it than what is supposed to be. Now if I agitate it or bump it or add a seed crystal, now all of a sudden a whole bunch would precipitate out or be a solid that forms. There would still be some dissolved in there, but all of this right here would form a solid and then be removed from the solution because I agitated it or caused it not to be supersaturated anymore. Watch out for those trick questions on the upcoming assessment. Gases, generally solubility decreases with temperature. As you can see in this graph, solubility and temperature. As temperature goes up, what happens to CH4, O2, CO, and HE? Notice it generally goes down. This is important for people that live in Minnesota because we like to fish in lakes, and lakes have fish in them that like oxygen that comes out of the water. When the water gets warm, what happens to the amount of oxygen available in the water? There's less and less, and every once in a while you hear of a fish kill because they don't have enough oxygen in the water, and that's usually because the water temperature gets too high and not enough oxygen can be dissolved in it. That's why trout are animals or fish that usually need a lot of oxygen, like to live in cooler temperature water, or at least water that's moving a lot where more oxygen can get dissolved in it. So solids generally increase solubility with temperature. Gases generally decrease solubility with temperature. Last thing of the day, different types of solids. For this, you need a periodic table. On your periodic table, we'll go through each one of these types of solids. Ionic, two types of covalent, metallic, and amorphous solids, and give you some very, very general rules about these things that you'll be able to answer. First of all, find the metals on your periodic table. The metals. Find the metals. Okay? On your periodic table, the metals are the ones that are over here on this side of the periodic table, and they include all of these bottom ones down here, and then they go up this like little staircase right along here, up this little staircase. So all of these would be the metals. That means sodium's a metal. That means potassium in your bananas is a metal. That means zinc's a metal. That means tin and lead, they're metals. Aluminum's a metal. Now, if you take a metal and put it together with any non-metal, remember the non-metals are over here. These are all the non-metals, including hydrogen. Hydrogen's a non-metal. If you put a metal together with a non-metal, you have an ionic compound. Ionic compounds are generally really high melting points. They're stuck together by ionic bonds, which are super strong. They're difficult to break apart. These ionic bonds are an intramolecular force that has to be broken to do any kind of phase change with them. Super strong. Second kind, covalent substances. Regular covalent substances are what we've been studying all in chapter 11 and 13. They're two or more nonmetals stuck together. Things like CO2, things like CO, things like CH4, things like C6H12O6, glucose. Those are all regular covalently bonded things that are held together by the intermolecular forces, London dispersion forces, dipole-dipole forces, maybe even hydrogen bonds. H2O would have hydrogen bonds. Okay? That's regular covalently bonded things. These forces right here govern whether or not they're going to change phase. A special kind of covalent bonds are ones with what are called covalent networks. In this class, all you need to know is a couple of covalently networked bonded items. Silicon dioxide, also known as sand, is one of them. Carbon in one of its forms is called diamond. These are covalently networked. These are super strong covalent bonds, and those are giant molecules that are formed together with these covalent bonds. They have really high melting points. They're usually really hard. They're usually super strongly stuck together. It's difficult to melt sand. It's difficult to melt diamond. Why? Because they've got these covalent network bonds. Know these two items and you'll do well in the assessment. Metallically bonded things, this is what holds pure metals together. What holds copper together? Metallic bonds. What holds iron together? Metallic bonds. What holds nickel together? Metallic bonds. What holds chromium together? Metallic bonds. What holds metals together? Metallic bonds. they have lots of free electrons, and those things allow it to be good conductors of electricity. Usually gives them luster so they can be really shiny because of the unshared electrons. Amorphous solids, these are ones that have usually been melted and then they're frozen together in a state. A good example is SiO2 when you melt it and then it freezes again. If you melt sand, you can make something called glass. Glass is an amorphous solid because the SiO2 molecules have been agitated and moved around and then frozen in place. This frozen in place is called an amorphous type solid. Know these categories of solids, you'll do great on the assessment.